Hey everybody, good morning. Welcome to SMathHacks. Before we get started, I wanted to see a raise of hands of who has never participated in a hackathon before. Great to see on both sides. So yeah, welcome to SMathHacks again. This is NCSSM's annual hackathon. This is our 6th year running. We're going to have a weekend of innovation, food, and fun. You guys are going to code, make, and present a bunch of projects. You guys will get to see a bunch of new people in the field of space and aeronautics. And this is going to be a great experience for anybody who has already participated in a hackathon, as well as people who have never even coded. Let's take a look at our schedule today. On Morganton, right after this ceremony, we're going to take our picture, and then we're going to have breakfast. We're going to have one workshop, and then we're going to have lunch at 12:30. Then we're going to have 3 more workshops back to back. And then I want to point out at 4 o'clock, we're going to have a project submission instruction Q&A session, and everybody is required to attend this event. For Durham, it's going to be in the ETC lecture hall, and on Morganton, it's going to be in the AC stairs. Online students, please join the Zoom link. It should be the same Zoom link for the workshops, and we'll make sure to guide you to the right place. At 4:15, once the project submission Q&A session is done, we're going to have a special session hosted by Mr. Bobbert. It's going to be the Entrepreneurship Opportunities in North Carolina event. This is also required. It's going to be in the same place right after the first session. And then after that, you guys are welcome to work on projects until 10 o'clock. So for our tracks, so our theme is going to be space and aeronautics this year. Our tracks are going to be web and mobile applications, hardware, explanatory modeling and computational sciences, AI, and machine learning. There's a bunch of descriptions on our website, so please make sure to check that out, not only for the descriptions, but also for project examples that you may want to look at if you're having trouble with forming ideas. So when you're competing in the tracks, there are going to be prizes if you win for first, third, and second. The Snoopy plush and the DoorDash Amazon gift cards are for raffles. And to enter into those raffles, all you have to do is attend the workshops. For every workshop that you attend, you're going to get 1 entry to the raffle. So if you want a better chance of getting the prizes, then make sure to attend as many workshops as you can. And there are multiple of these, so it is for, I think, 10-ish people. Now for the Durham location information. For Durham participants, you guys are going to stay in the ETC and Second Bryan. All your food and co-working will be in Woolworth. The workshops will be in the dry lab, and if there's too many people in the lab, then you guys are going to move to the E-lab, and any additional work area is going to be on Second Bryan. For Morganton, everybody make sure to stay in the academic commons. If you need any drinks, you can visit the cafeteria fountain at any time you'd like. Just make sure to have your badge on to make sure that the workers in the cafeteria know that you are a SMathHacks participant, and you're welcome to grab any of the drinks at any time. All the catering and food will be in the smart bar area. So anytime we have breakfast, lunch, make sure to go there. The workshops are going to be in the Fab Lab, and the TAs are going to be in the Leviton. Half the AC is reserved, so you guys are free to roam anywhere you'd like on half of the AC. For virtual students, all the Zoom links will be on the schedule. And for the keynote speaker, we have one special webinar link. For all the workshops, it's the same. It's a different link, but it's the same for all the workshops. And when you join the workshops, you will be guided by one of our other leads to either go find a TA or to join the workshop session. And that's what the breakout rooms are for. Now for submissions and for teams, the deb post where you can post your submission for your project will be emailed out soon during breakfast, I believe. And I just want to note that any team members should be added to the dev post if you're submitting together. If you don't have a team yet, feel free to uh, talk to others and see if you can join their teams. And if you want to work alone, then that's fine too. Just a reminder, at 4 o'clock, we're going to have our project submission, instruction, and Q&A session, and at least one person from each team is required to attend, but the second session, right after for the entrepreneurship, is required for all participants, so all of you might as well come. If you need any help, feel free to email our SMathHacks email. It's smathhacks@ncssm.edu. We will make sure to get to you and answer your question right away. If you're in person on Durham or on Morganton, feel free to find me, to find Charlotte or any of our leads or our advisors to ask any type of questions ranging from like how to do a certain code or how to access the schedule. Quick thanks to our sponsors as well as our advisors for helping us fund this event, helping us plan this event, and really making it possible for this event to even be. Now I would like to introduce Mr. Nicholas Lima. He earned a bachelor's degree in aeroscience and aerospace engineering from Massachusetts Institute of Technology. While in school, he operated MIT's nuclear fission reactor, and after graduating, Mr. Lima became an engineer at SpaceX. There, he helped to build and test the first private spacecraft to take astronauts into orbit and to the International Space Station. Mr. Lima is currently the Vice President and Engineering at Helion Energy, where he's working on harnessing fusion energy to deliver clean and inexpensive and abundant electricity to the world. So please welcome Mr. Nicholas Lima.
Can you guys hear me okay? Sweet. I'm getting thumbs up from there also. I am here talking to you today because about 16 years ago, Mr. C, who I think a lot of you know, was my high school computer science teacher. I'm very excited to talk to you. I think I was trying to think of sort of what messages would I want to share that you might find interesting. And I ended up doing a lot of show and tell. So I want to tell you guys about some of the exciting stuff that I feel really lucky to have worked on and to be working on, and sort of how I feel like I kind of fell into it a little bit, and then answer any questions that you have about any of the work that I've done, or anything else. And I am going to try to leave like 15 minutes for questions. So, like I said, I did a lot of computer science and physics and math in high school, and then going into college, I always sort of knew that I wanted to work on rockets or spacecraft, and the way that I sort of applied that was at the time SpaceX had just launched their first cargo carrying spacecraft to the space station. So this is uncrewed, nobody on board, carrying food, supplies, experiments to the International Space Station. And they had also just started an internship program, and so I was trying to get summer internships at SpaceX. And one of my messages here is, I want to communicate to all of you that I definitely don't feel like I was successful in everything that I've tried at all. And this is sort of one of my examples. My freshman year of college, I applied to an internship at SpaceX, and I heard absolutely nothing back, which is pretty demoralizing to be like, hey, I really want to be working on this thing, like really putting your all into an application for something, and then just hearing nothing. My second year of college, when I was a sophomore, I applied for an internship again. And part of the sort of application was you could submit a video. And so definitely the most embarrassing thing that exists about me on the internet is if you go on YouTube and you search why I should work at SpaceX, there's a video of, 19-year-old Nick showing off like a telemetry system that I was making for a model rocket. So it sort of had a GPS antenna, had a radio to talk to my computer on the ground, and sort of send data from the model rockets I was building back down to the ground. And I heard absolutely nothing back that year either. And then junior year, I applied again, and that was the first time I had heard anything back from them. And so after my junior year of school, I like flew out to LA. I'd never been to LA before, and started working at SpaceX. And what I was working on was there was a rocket in Texas, and basically what SpaceX was trying to do, and I'll talk a little more about this later, was the rocket that SpaceX flies right now has two stages, it's called. So you have a first stage, and they're essentially, when I say first stage, second stage, essentially two different rockets sitting on top of each other. And the first rocket gets you from the ground most of the way into space. But in order to actually get into orbit, you don't just need to be high enough. You don't just need to be in space. You need to be going fast enough that you actually stay in orbit around Earth. So the first stage gets you sort of out of the Earth's atmosphere, and then the second stage, another rocket that has whatever you're flying on top of it, gets you from that spot really high up actually into orbit around Earth. And what SpaceX was trying to do was land their first stage. So to give you sort of a sense of how much hardware to get things into space costs, the first stage of a SpaceX rocket right now is probably around $60 million. The second stage is probably around 15, 20. And so prior to the work that SpaceX was doing to land that first stage, every time you flew anything in space, you would throw out that first stage. So if you think about the cost of sending experiments, satellites, anything into space, every time you wanted to fly anything in space, you had to pay for the entire rocket because you were throwing out that entire rocket every flight. So what we were trying to do was practice basically hovering a rocket and then having it come down slowly and do a controlled landing. What I was working on as an intern was just one like tiny little piece of that, which was there were a bunch of high-speed sensors on the rocket. So these are, think like accelerometers, for example, like measuring vibrations in different parts of the vehicle. And I was there wasn't enough like room on the flight computer, like literally not enough ports to plug in all those sensors. And so I had like a little file server off of Amazon that was like zip tied to the side of the rocket and had a bunch of cables running to it. And then when the rocket landed, I had software that would run and pull the data from that little file server and sort of send it to all the engineers who wanted to look at it. You guys could probably do that now in a weekend. You could go and do that project. But that was what I spent my summer working on. And this was the last day of my internship. So it was the last day of my internship. I was like literally going to the airport later that day. And I got to, they asked me, like, do you want to sit in mission control and actually get to like, when the rocket lands, like press the button to start your software and have and like actually do the data download. And so obviously I was extremely excited to do that. And then this was the result. The rocket exploded like a couple thousand feet in the air, and my entire summer project never got to do anything with it, which I think is it's a good, again, I'm going back to one of the lessons I want to share, which is it's okay when stuff fails if you keep trying. Like things like whether it's rockets, whether it's applying to internships, like it's okay to not get it right the first time, as long as you're learning from those experiences. So this was an interesting one where what actually happened was everything on rockets and spacecraft is what the term is like triplicated. So if you have one sensor measuring something, instead of having one, you'll have three. And the reason for that is if one of your sensors fails, you'll have the two other ones, and they can basically vote. So you can say what's the pressure in my rocket engine, and take three measurements, and then say which two are closest to each other. Those are probably the correct ones. And so on this rocket, we just hadn't installed all three sensors. There was only one sensor in the engine, and it broke, and it caused the vehicle to destroy itself. So it was a good lesson. After school, so this is, I wanted to sort of show you what I was talking about earlier. You can see from the ground up to that first black section of the rocket. That's the first stage. So most of the rocket is that first stage, just to get you out of the Earth's atmosphere. And then there's a tiny little section in between that first stage and the spaceship that's sitting on top. And that's the second stage, to actually get you into orbit. And then what I spent most of the rest of my time at SpaceX working on was the little spaceship sitting right at the top. It's called Dragon, and it takes cargo, and eventually took and takes now astronauts to the space station. So here's a picture of Dragon, and I'm gonna go through a little bit of some of the projects that I worked on. So I went back to SpaceX full time, and somebody said, "Hey, you worked on that data recorder project for the rocket that blew up." And I was like, "Yes, that was me." And they were doing a test of the Dragon spacecraft where they were testing its abort engines. So one of the things that the vehicle does that is super neat is, imagine a situation where you launch your rocket, you have astronauts sitting on top of it, and something goes wrong with the rocket. You want to be able to basically rip your spaceship off the top of the rocket and get it far enough away that even if the rocket is exploding, you can keep the astronauts safe. So that's what these rocket engines on Dragon, which sits on top of the rocket, are meant to rip the capsule away from the rocket. And basically, I got to take that same project that I had done as an intern and do it again for this test. So really took what I had done in an internship and just directly apply it to the start of my work. I then worked on a project called, okay, there's a lot that goes into a spacecraft that is not sort of what you typically would think of if you're trying to get people into space. So not only do you need to be able to, rip your capsule off the top of the rocket and get your crew to safety, and sort of have the spacecraft be able to maneuver in space, dock with the space station, you also need to be able to keep people alive. And there are problems that don't sound like aerospace engineering, right? Like, how do you maintain oxygen in a closed space? How do you get rid of the carbon dioxide that people are making? How do you keep the humidity correct when you have a bunch of astronauts in there sweating? And so the next project I worked on was called the Life Support Systems module. And so this was a test of Dragon's life support systems. So you can sort of see the same shape of the spacecraft. And then on the inside, we had all the life support systems. So we had tanks of oxygen, we had carbon dioxide scrubbers, we had dehumidifiers, we had an air conditioning system, and we actually put 4 people inside of this. So one of the problems that we were trying to wrestle with was, how do you, okay, we have this test bed. How do you actually simulate having people, breathing the air inside, sweating? And we spent a ton of time thinking about, do we have something that scrubs oxygen out of the air inside so that we can show that the system can put oxygen back in? And then we inject carbon dioxide, and we have a humidifier. How do you go and actually test a system like that? And what we came up with was the easiest way to do it was just to put 4 people inside and tell them to do squats for half an hour. So we did a big test for NASA where they showed up at SpaceX, and we had sort of 4 of my friends inside of this capsule And we just told them to sort of exercise as much as they could in the confined space and show that the spacecraft could actually kind of make up for it. And my favorite, one of my favorite little tidbits from this test is you can see right here what looks like a home smoke detector. The night before the test, we were sort of staying up super late doing all of our final system checks, and somebody said like, "Hey, we haven't actually tested the smoke detectors in the spaceship, sort of with smoke moving around the cabin." And so we went inside and we like lit some paper on fire, and we found out like the night before this big test that we were doing for NASA to prove that we could keep their astronauts safe in space, we found out that our smoke detectors did not detect smoke. And these had been like worked on for several years. It was like a huge miss on our part, but we still really wanted to do the test. And so we had to kind of like, how do you scrappily figure out, you need a way to detect smoke? You run across the street to Lowe's and you buy a bunch of home smoke detectors, and you put them in your fake spaceship. There are a bunch of these are. I didn't have a video of this, but there are four SpaceX engineers who we made do squats in there for an hour. So while that was going on, there was another spacecraft that was built that went to the space station with no people on board. So all of the stuff that we were working on inside the spaceship, a different team was building a spaceship that didn't have any of that stuff on the inside, but had everything it needed on the outside to actually make it to the space station. And it did. So it went to the space station, showed that Dragon could successfully dock, showed that Dragon could get away from the space station safely, re-enter Earth's atmosphere and land. And then, like I mentioned before, we really wanted to be able to show that the spaceship, if something were to happen on the rocket, could rip itself off the top of the rocket and get the astronauts to safety. And so this vehicle that went all the way to space, engineers spent probably like 5 years building it, came home, was then going to be used in a test where we flew it on top of a rocket and actually like broke the rocket to show that it could actually get itself away. And so we'll see if this this is a video that somebody took on their cell phone. So before getting ready to put that vehicle on top of a rocket, do that huge integrated test, first we needed to make sure that the propulsion system was sort of still functioning, right? After the vehicle had been to space and back. See if this plays. So again, this is, imagine you're an engineer in mission control watching this thing that you've spent, put 5 years of your life into just evaporate in a fraction of a second. So what had happened there was a tiny bit of metal dust in the propulsion system had sort of flowed with the fuel, crashed into a valve, and because the fuel that these spacecraft use it's so volatile, it's like so easy to get it to burn. Just those metal particles in the fuel crashing into a part of the piping was enough to ignite the entire fuel system and destroy the whole spaceship. So we learned from that. Took us about 6 months. So we had a bunch of spaceships in different sort of stages of being built and tested, and we had to take them all fully apart and totally rebuild the propulsion system. So that couldn't happen. And so this vehicle, this is sort of what the bare bones look like, the structure of the spacecraft, and some of the propulsion system. This vehicle went on to do that test that I was talking about. So you can see the rocket mid-flight, and you can see the spaceship lighting those same engines from that earlier picture and actually ripping itself off the top of the rocket, and then the rocket exploded. And you can actually go watch that whole video. So up to this point, again, I've showed you like a lot of us messing up, like making small mistakes, learning from them, um, and sort of, moving on and trying again. This was like 2018, 2019. This is when we really got to the point where that changed. So all that time of it being okay to mess up kind of went away in a heartbeat when these two guys showed up. That's Bob and Doug. And they were the first two NASA astronauts that we were going to fly to space. And they came and they visited us. And my main memory from their visit was, we were, I don't know, a bunch of like 25-year-old engineers, and they showed up, and somebody asked them. So when astronauts go to the space station, they get a bag where they're allowed to just put whatever they want in it. So most of their stuff is totally planned out by NASA, right? They have like exactly how many like pairs of clothes do they have, exactly how much toothpaste do they have, but they get one small bag where you can just bring whatever you want to space. And somebody asked Bob, what are you going to bring to space with you? And I think that, we were all expecting like his favorite food or something like that. And what he said to us was, he said, I am going to bring my son's Buzz Lightyear toy to remind me that no matter what happens, I have to make it home. And that was a huge moment for us where we were like, wow, this is like the mindset has totally shifted, right? Like we cannot mess this up. We have to get Bob home to his kid. So it's a really, really interesting sort of shift from it being okay to mess up to really needing to be super confident that everything that we were doing was gonna work perfectly, sort of the first time that we were doing it for real. And we did. These photos are from 2020. So there's Bob and Doug coming onto the space station. There's the spaceship as it was getting ready to dock with the space station. And that was really the peak of my time at SpaceX, like getting to see a spacecraft from that sort of full evolution from, us messing around with data recorders that we ordered from Amazon all the way to actually having astronauts on the space station and seeing that full life cycle. I then started working on Starship, and I wanna explain a little bit like what Starship is. So when I talked at the beginning about the rocket that SpaceX flies now, the real thing that rocket has contributed to the space industry is landing that first stage and then getting to refly it. Um, and that means that every time you want to send something to space, you're no longer paying, $60 million for that first stage. Maybe you get to reuse it 6 times or 10 times, reuse it 10 times, and all of a sudden, instead of paying $60 million every time you send something to space, you're paying six, right? So Starship is sort of trying to take that to the next level, which is on the rocket that SpaceX flies now, when SpaceX is launching satellites or flying astronauts, that second stage still gets thrown out. It basically makes it all the way into orbit and then has to slow itself down a little bit. And there's a spot in the Pacific Ocean where everyone crashes their space trash. So every single time a rocket launches anywhere in the world, the second stage like falls into the Earth's atmosphere, breaks apart, and crashes into the Pacific Ocean. And there's like a rocket graveyard in the middle at the bottom of the Pacific Ocean. So the next step, in like really getting to cheap space flight is getting to reuse your second stage. And it's hard because it's going so much faster than your first stage. So that first stage gets you into space and then falls back down and you can land it. The second stage is all the way in orbit. So when it comes back down, it's hitting the Earth's atmosphere much, much faster than the first stage does. And so you have to be able to have a heat shield that allows the vehicle to survive that. That's what Starship is trying to do. So there's me down in Texas, um, building uh, the first Starship that did a belly flop, we called it, so that we would fly them up to like 30,000 feet, sort of how high commercial airliners go, and then show that we could control it on the way down and try to land it. Um, and this was really fun and really went back to that like go fast and break things mentality. So we blew up probably about 10 of these trying to land them. So we would fly them up to 30,000 feet, have them come down and control themselves, and then they would try to flip at the end and turn back vertical, and then touch down. And we basically every single month for 6 months we were flying one of these and breaking it and flying it and breaking it, and we would get so close. We had a few where they actually landed and they looked like everything was going to be fine, and then they tipped over and exploded. This was really some of the most fun that I've ever had, because it was taking that sort of very early, small scale, like build something as fast as you can, go break it, learn about it in the real world at a crazy scale. Like these are enormous rockets. Um, and then this is sort of the point where Starship is now, where they're now flying first stage, which is everything up to those little fins you can see sticking off, and the second stage all the way into space, and actually getting them to re-enter. And they haven't quite landed a second stage yet, but they're getting super close. So when I think about Starship, and what I think a lot of people don't really understand about it, is like the whole point is have every part of your rocket be able to go to space many, many times, so that the cost of sending anything you want into space is just, how expensive your fuel is. And all of a sudden, sending things to space is more like driving a car, right? You don't think about paying for your car every time you get in your car. You guys probably don't have cars yet, so that might be a really bad analogy, but you know what I'm saying. Um, yeah, so that sort of ended my time as an aerospace engineer. I loved SpaceX. I loved the work we were doing. Um, and I think maybe this is one of my other big messages is you guys should all really be trying to find stuff to work on that doesn't feel like work. Like find things that really feel like, this is very cliche, uh, but find things that you're excited to work on and then just go after them. And I hit a point a couple of years ago where what I was interested in really changed away from rockets, and I'll quickly tell you why. I saw a bunch of graphs that looked like this. So on the bottom is how much energy per year uh, a country, someone in a country uses on average, and then on the vertical axis, on this one, it's GDP. So think of it as like how much does the average person like contribute to the economy, right? And you can see that if you want sort of a wealthier country, a bigger economy, you need more energy. And I think there's a lot more to life than having a big economy. You can see this same graph for other measures of sort of how successful a country is. So maybe you care about life expectancy. Expectancy correlates with how much energy people use on average. Same thing with the UN maintains a metric that they call the Human Development Index, and it includes things like what level of education does the average person get to. It includes like measures of happiness, like asking people how happy they are, and it also correlates with energy use. And this is also true of if you just ask people how happy are you, if they use more energy, they're more likely to tell you that they're happier. And the thing that really connected with me was if we want everyone in the world to climb up those metrics, we don't actually know how to make enough electricity to do that. Like we don't know how to make enough energy in a way that doesn't really damage the planet and in a way that we can actually go make quickly. And so I shifted my focus of what I was working on to thinking about how can we go and make way, way more electricity for the world. Going back to college, I worked in college at a little nuclear research reactor. And when I explained to people what nuclear energy is, basically everything in the universe, every atom in the universe wants to be iron. So things that are heavier than iron, if you break them apart and get them closer to iron, they will release a little energy. Things that are lighter than iron, if you combine them and they get heavier and closer to iron, they will release a little bit of energy. So nuclear fission is taking heavy elements and breaking them apart. And when you do that, a little bit of energy is released. So this is what we think of when we think of nuclear power. The other way to go is doing what the sun does, which is taking really light elements, combining them, releasing a little bit of energy. Nobody has ever been able to do fusion, taking the light elements and combining them to get them a little heavier. Nobody has been able to do that on Earth in a way that produces more energy than it takes to get the reaction to happen. And that is exactly what I'm working on now. So I work at a company called Helion, and what we're doing is basically using magnets to try to get a plasma into a state where fusion is happening, and happening at a rate where more energy is being produced than we're consuming to get the plasma to do the fusion. And this is sort of when I think of what I liked about rockets was how sort of multidisciplinary the problems were, right? Like I didn't know how to decide, do I want to be working on software? Do I want to be a mechanical engineer? And the nice thing about rockets is you get to kind of do all of it, right? All of the problems are mechanical and there's physics and everything is using software. And this takes fusion sort of takes that to the next level where in addition to all of that, you have crazy electrical currents, crazy magnetic fields. The plasmas that Helion makes are about 6 times hotter than the sun. And the machine that we're making right now that I have a picture of is going to go like far beyond that. Like we'll be like 20 or 30 times hotter than the sun in that plasma in the center of our machine. So this is a very early machine. This is from like 2012. And you can sort of see what happens is on either end, we make a plasma. That's that glowing pink that you see. We then slam them into each other in the middle and hit them with a really high magnetic field to compress that plasma to get it hotter and denser so that fusion happens. And we're doing sort of exactly that same process of like telling ourselves it's okay to be wrong about things. It's okay to break things. It's like how fast can we build a system, go really learn about it in the real world, see what problems we never would have guessed, see how it compares to simulations or modeling that we're doing. So this is a machine from 2012. This is the last machine the company built. So this is around like 2019, 2020. So much bigger. It's just a cool plasma picture. And then the machine that we're building now, we just started to make plasmas on. And later this year, we're hoping to show that we can actually get electricity out of it. And if we can do that, we're going to go and learn the lessons from it and go build a power plant as quickly as we can. And if we can do that, we're going to go just build as many power plants as we possibly can and put them all over the world to really go try to solve the problem of how do we just get more electricity to humans all over the world to use for whatever they want. That was what I had. I'm super down to answer any questions. And I think how that's going to work is you should scan that QR code and you should enter your questions. Uh, and then they will get given to me and I will read them back so everyone can hear them. Thank you. We could also just cause chaos. And if someone has a question while people are writing questions, you could just ask me and we could start. Yeah. Yeah. Yeah, so the question was thinking about when I was working on Dragon, this is also very important for Starship. Uh, like what systems are available and what are the trade-offs for deciding what to use for reentry. So the or to protect the spacecraft during reentry. The answer there is one, absolutely. And the trade that you're making there is every pound that goes into a system that is protecting the spacecraft during reentry is a pound that you don't get to send to space, right? You have to you if you have heat shield tiles, for example, you're carrying the weight of that all the way into space, all the way into orbit and back. And so it is literally a one for one trade of if your heat shield, weighs 101 pounds instead of 100 pounds, that's 1 pound that your satellite can't weigh. And so that's the main trade when it comes to protecting spacecraft during reentry. And the systems that people use mostly, um, they use like a ceramic. It's like a tile that gets it's like a liquid and then gets baked. And they're very lightweight quartz glass. It's like quartz is like a rock that you can find. Um, the people mine and then they grind up and then they make little glass fibers and they pour it into these tiles and it's honestly very similar to like the insulation in the walls of your house. And that's what gets used. And the downsides there are so it's really light, so that's good. The downside is it gets eaten away as you're re-entering, and so it's not really reusable. So on dragons get flown, I don't know how many times they've probably 5 times maybe, and every single time they have to remove the whole outer surface of the vehicle and install new insulating tiles. So there are people working on systems that are fully reusable for heat shields. Most of it is like cooled metals. So you get a metal that can go to a really high temperature, and then you have to flow really cool liquid through it. So it's harder on spacecraft, but on rockets, that's pretty doable because the propellants that you're using on any of these big rockets are at very, very low temperatures, like well below freezing. And so you can use those, and on the way to the engine, you flow your coolant or you flow your propellant like through your metal heat shield, and you cool it off, and then the propellant flows into the engine. So a lot of people are working on that. There's a company called Stoke Space that you could go read about that's in Seattle and working on that problem. Yeah. Should I just go from the top? Oh, this is a good one. We have a lot of upvotes to what's the most embarrassing thing you know about Mr. C. I'm gonna think on that one and then come back to it so that I can come up with something really good. How did the learning opportunities at MIT help you in your career? This is really interesting. Um, I will tell you, I said this to Mr. C last night. MIT is an amazing school. I don't think that just going to MIT and taking classes actually makes you a very good engineer. MIT is very, very sort of theoretically focused. Um, and so a lot of the engineers who come out of MIT haven't actually built things themselves. They are very good at math, they're very good at coding, but they haven't actually had to make systems in the real world. Oh, sorry. And so I think one thing that I would highlight there is the importance of things like what you guys are doing today, where you actually have to go try to do something not in a classroom, right? It's not a like find those opportunities that are not well-defined problems that you're doing as part of homework, but where you can really think outside of the box and just be like, my only constraint is I need to make something and it needs to do a thing. I think that's where you get a lot of where a lot of learning that really prepares you for engineering in the real world happens. The question is, in a fusion reactor, if the plasma is heated to the six times hotter than the sun, how is that heat controlled inside the reactor? This is a very good question. So what happens is, do you guys know what a plasma is? So if you have a gas, you have a bunch of atoms floating around, and then if you heat it up enough, it will turn into a plasma, which just means that your electrons and your nuclei, like the center of your atoms, have so much energy that they're not bound to each other anymore. And sort of you get this soup of electrons and ions. And the interesting thing about that is you guys may have talked about this in physics, but so if you have electricity running in a circle, it creates a magnetic field inside of it. That's how a lot of like valves in your car work. I'm going back to cars. Sorry. So you run electricity in a circle and you create a magnetic field. An interesting thing about ions and electrons, when they're free to move around, they'll orbit magnetic field lines. So if you have a magnetic field, they will sort of just spin around it and go back and forth. And so how we get away with having a crazy hot plasma without it just instantly melting the walls of our machine is our magnetic field actually makes it so even though the plasma is at crazy high temperature, it never touches the wall because we have a strong enough magnetic field that we keep a gap. And when we design these systems, we keep a gap of about like 4 centimeters between the plasma and the wall. So even though the plasma is really hot, it's not actually giving most of that heat to the wall of the machine. Um, it is radiating heat the whole time. So you're still heating up your machine and you still have to deal with that heat, but not as much as if the plasma was actually allowed to touch the wall. This question is, did you do model rocketry in high school? And if so, what were your favorite experiences? I did do model rocketry in high school. Um, I think my favorite experience there was I got a bunch of friends and we all thought we were going to be really good at it. And we started a team to go there. There is like a national high school rocketry competition. And we started a team and we spent months working on a rocket. And I think the challenge was like, can you get it to go to a really precise height? And so people would do crazy things to sort of like add drag to their rocket to get it to stop at like the perfect height. And we went and tested our rocket, and we were kind of planning on, we're going to test it, we're gonna modify the design, and then we're going to go to this competition, and our rocket just totally blew itself apart, and then just kind of rained debris. We had gotten like a bunch of friends out and a bunch of teachers out to watch us fly it, and we just like rained pieces of rocket on everyone. Which I think is again probably my favorite. That was my favorite experience because I think it was a good lesson for us in, you know, uh, Humility. So the question is, do you think access to nuclear fusion will be expensive in the future, or will the costs be available to most people? This is a really, really good question, and something that I spent a lot of time thinking about. And the way that I think about it right now is that uh, I have two thoughts. One is like the first light bulb was pretty expensive. Um, like a lot of development time, a lot of failed experiments went into actually having like the first light bulb in a home. And that made that light bulb very expensive. Now we don't think about the cost of light bulbs that much. So one side is I think that if we can actually unlock creating electricity in this way that humans have never done it before, uh, there will be a lot of work that goes into making it cheaper. The other side is we actually do think about that when we're designing these systems. So I think it's that's another sort of very important engineering lesson is like really understand the problem you're solving. Don't just like do the tasks, but really try to understand what are you trying to solve for. And so when we think about systems that we're designing, uh, the metric that we use to be like, did we do a good job designing a fusion machine is not how much fusion it does. It's not how hot can we get the plasma. It is like what will the cost of electricity coming out of the machine be, and how do we go optimize everything we do in our design for that. And the reason that I believe in that a lot is sometimes when people are talking about deploying new types of energy, whether it's solar, wind, nuclear, um, if it's more expensive than how people are getting their electricity now, nobody's really going to want to go deploy a ton of it really quickly. And so to me, if you want to have people using more energy, and you want them doing so in a way that is sort of clean for the environment, you have to you have to you have to incentivize people to want that energy. So again, when we're designing these systems, like that is the metric that all of our engineering work goes into. What is the cost of electricity going to be when we're putting it on the grid from one of these systems? And that like impacts the day-to-day decisions that we're making in our engineering work. Yes. What kind of math-related jobs does SpaceX offer? Is there any sort of theoretical computer science or algorithms work involved? The answer is definitely yes. Um, there are a ton of jobs like that at SpaceX. SpaceX obviously does a lot of hardware. When I think of algorithms at SpaceX, um, a good example from what we were talking about is when the spaceship has to rip itself off the top of the rocket, all those different rocket engines around the spaceship are all independently throttleable. And I'm friends with the person whose job for several years was modeling the control algorithms for the vehicle ripping itself off the top of the spacecraft. So I don't know if I would call that uh, that is very like algorithm heavy. I don't know if I would call it like theoretical math, but very algorithm heavy. Where some of them maybe, or like very controls heavy. There are other problems that SpaceX is solving, that I think are sort of pure computer science algorithms problems. Like SpaceX now has thousands of satellites, uh, giving people internet on the ground, right? And if you have a Starlink dish pointed at the sky, the SpaceX satellite network has to decide like which satellite is going to be talking to you, and they have to decide that for millions of customers at the same time to like optimize for how many customers they can support. When I think about problems like that, those are really sort of pure computer science. we could like distill it down so that it's just an algorithms problem that looks exactly like problems you guys have seen in classes. Last question. I'm still thinking about that one. Could you apply your current work to other problems around the globe? Instead of energy, why not water, food, medicine, education? Absolutely. And I think part of the reason that I left SpaceX was because I felt like we had gotten really good at this sort of like rapid iteration. Like go design something, go build it, go test it, learn what you didn't really understand about it by seeing how it breaks. And I really wanted to apply that mindset to other problems. And I picked energy because I was interested in it, but I think that that same mindset could be applied to anything that you're interested in. So if you see a problem, you're interested in solving it, think about like what is a solution that I could go and go build something and then see if it works and learn from that. And I think that could definitely apply to any problem, not even problems at all related to science or engineering. Thanks, everyone. I really appreciate it.